Hello and welcome back. It turns out that you can differentiate a series term by term, and that new series is going to have exactly the same radius of convergence and interval of convergence, except possibly at the endpoints of the interval. So in example 3, when we're asked to find a power series representation for 1 over 1 minus x squared and find its radius of convergence, well, what we could do is start by noting that the derivative of 1 over 1 minus x is equal to 1 over 1 minus x squared. Let me write in the derivative there. Forgot to write that in. There we go. So the derivative of 1 over 1 minus x is equal to 1 over 1 minus x squared. Just to note that at the beginning. Now it's not really like the first thing that may come to mind, but just because we've been in this section and we know what the power series expansion for 1 over 1 minus x is, that's going to help us get a power series for 1 over 1 minus x squared. Because 1 over 1 minus x looks like this: 1 plus x squared plus x cubed plus, and so on. So if we take the derivative of that, which is just like taking the derivative of the series as n goes from 0 to infinity of x to the n, so if we take the derivative of this series expansion for 1 over 1 minus x, that would give us a series expansion for 1 over 1 minus x squared. Right? Because the derivative of 1 over 1 minus x is 1 over 1 minus x quantity squared. So all we have to do here, based on that note above, is just differentiate term by term the power series expansion for 1 over 1 minus x. So the derivative here of 1 would be 0. The derivative of x would be 1. So actually I'm going to write that 0 in there just for reference. 0 plus, and then derivative of x is 1. And then we've got 2x. Then we have 3x squared, and so on. Just keep taking derivatives term by term. Now what this is going to look like in the series is something like this. Oops, I wrote that a little too early. It's going to look like nx to the n minus 1. Now you can either think about this as like, what's the pattern of these terms, and you'll notice that the pattern is, well, the coefficient goes 1, 2, 3, and so on, and the exponents are 1 less than the coefficient. So then you have n times x to the n minus 1, where n starts from 1 and goes to infinity. So you can either think about it like the pattern, writing the, from the pattern, write the series expansion, or you can just think here the derivative is going to work its way into all of these x to the n's, and when you take the derivative of x to the n, you get n times x to the n minus 1. Literally that power rule for derivatives. Now the one thing that's a little detail here is that the first term, which is 1 here, the derivative of that is 0. So we do have to take that into account. Like that first term is a constant whose derivative is 0. And so because the derivative of that constant makes that first term disappear, right, because it becomes 0, then the n, the starting n value, is going to increase by 1. You're no longer going to start at n equals 0 because there is no n equals 0 term to speak of anymore. So it'll increase to n equals 1. So just a little detail there to think about. But there's the power series expansion for 1 over 1 minus x squared. Now one thing is, it says find the radius of convergence. Well, if we can find the radius of convergence of the original power series of 1 over 1 minus x, then it's going to be the same radius of convergence for the derivative. So remember that the radius of convergence for the power series x to the n is going to be, well, there's the interval of convergence, and the radius of convergence is 1, right? Because it's going to converge for all x values between -1 and 1, so the radius of convergence there is just 1. It's halfway across the interval of convergence. And so our radius of convergence for this series is 1 as well. Same as the original. I should write the series actually. Okay, so that's pretty cool. It did take a little bit of looking at and thinking, okay, well, how can I rewrite this as the derivative of a function whose power series expansion I know? And so it felt a little bit hacky, but at least it gives you an idea that you can take the derivative of a function of a given series, and you'll be able to do that term by term to get the power series expansion for the derivative. Same thing for integrals. You can integrate a series term by term, and the result is going to have the same radius and interval of convergence, except perhaps at the endpoints of the interval of convergence. So example 4 says, find a power series representation for ln of 1 minus x, and find its radius of convergence. Now here we're going to have to think, okay, what's the function whose integral is going to give you ln 1 minus x? And that one turns out to be negative 1 over 1 minus x. If you integrate negative 1 over 1 minus x, you're going to get ln of 1 minus x. So if you integrate this, that's going to give you ln 1 minus x. And then you could just work it backwards. You could say, okay, well, if I took the derivative of ln 1 minus x, you'd get negative 1 over 1 minus x. So integrating negative 1 over 1 minus x gives you ln 1 minus x. But now we have this function whose power series expansion we know exactly what this is, because we've used it many times now. And so we're going to be able to integrate that power series expansion term by term to get a power series representation for ln of 1 minus x. It's because these two are equal. Well, actually, there is a little before I put the equal, there is a little plus c to worry about here. The integral here is going to have a plus c, so we're going to have to figure out how to deal with that. Let's do that first. Well, what we could do is write this out as negative and then 1 plus x squared plus x cubed plus ... We could also write it as the integral of the power series expansion. So this is a negative that we could pull out in the front, the sum of x to the n. And we could write the dx. Now, if we integrate term by term the expanded version of the series, we're going to get the negative sign we can keep out in front. We're going to get integral of 1 is x, integral of x is x squared over 2, integral of x squared is x cubed over 3, and then plus x to the 4th over 4, and so on. But we have a plus c. There's the most general antiderivative of this function has a plus c, has a constant that you could add to it, and no matter what the constant is, the derivative, if you turn back around, will be this power series expansion. So we're going to have to figure out what that c is. Over here, we could also work the integral into the x to the n, and you would add 1 to the exponent to give you n plus 1, and divide by that new exponent. So this would become negative n goes from 0 to infinity of x to the n plus 1 over n plus 1. And then we'll put a little parenthesis around here saying the negative applies to everything, although that's kind of optional, but it helps to distinguish between that and the plus c. The plus c is outside of the series. You could put the c in the front of everything if you wanted. You could put the c in the front for clarity. Notice, by the way, that the n still started at 0, and that's because you still have the n equals 0 term. When you integrated the n equals 0 term, you just got x. So we didn't lose any terms or even gain any terms except for the plus c maybe, but that's outside the series. So when you're integrating, you don't really have to update the starting n value. Well, let's figure out what that plus c is. We're going to find c. The way we're going to do that is by plugging in x equals 0. X equals the center in general. The reason that's good is because then our power series expansion is going to be 0, right? If you plug in the center, every single term becomes 0, and when you add them all up, you just get 0, so it's going to collapse into just c. But you could also plug in x equals 0 into the ln 1 plus x. That's what we're going to do. We're going to plug in 0 on both sides, both the function and the power series. There we go. Now on the left you have ln1, which is 0. On the right, again, this whole power series becomes 0, so you just have c. So c equals 0. So then you could say ln 1 minus x equals this power series expansion. If you want, you can bring the negative in, or you can leave it out. There it is. Now, once again, the radius of convergence will match the original power series' radius of convergence, which we already mentioned above was 1. And so this is also going to have a radius of convergence of 1. R equals 1. Great. Thank you so much for watching this video, and see you next time.